So today we are going to talk about rocks and minerals. So this module covers a lot of information. And so I'm going to try and give you the basics. So that means I might skip over some things. If you've had physical science, geology 101, then you've probably been introduced to this and this would be a good review. But certainly there's not a requirement that you've taken 101 to take Geology 110. But the focus of this class is on the disasters and the environment. And although rocks and minerals are important for geology, we want to focus on the hazards and how we mitigate those hazards and prevent loss of life and damage and things like that. And so we don't need to know everything about rocks and minerals, so we just need to know the basics. So that's what we're going to try to accomplish in this week's module. So this first slideshow is going to introduce you to minerals and then igneous rocks. And like I said, it's going to be a little fast and furious here. So, oops, let me not do that. So the first thing we want to talk about is, it's all related here. So the very first thing we're going to talk about is atoms. And even though that's not in the title, we need to know that atoms are what make up everything. And we know that there's a specific amount of atoms out there, and we know that these atoms and elements have specific properties. They can bond together to form new things, molecules, and some of those molecules end up being minerals. And if we take a collection of minerals and put them together, we get rocks. So that's kind of the progression that we see. And so we could look at a little diagram like this where we have a mineral, let's say quartz. It is composed of silicon and oxygen in a specific ratio, but those are the atoms. When we combine those, we get quartz, and then if we take quartz and a couple other minerals, we can create a rock called a granite. And so that's kind of the relationship between atoms, minerals, and rocks. And so as a really quick review, we just want to kind of go over what is an atom. And so you've probably seen this in your high school science class, but they're obviously very small. So we have diagrams that we use to kind of illustrate what's happening there to help us understand. So you've probably seen something like this, which is a very simplistic model that we can draw on a piece of paper. It's probably more like this other diagram here. But the idea is that there is a nucleus, and within the nucleus we have protons and neutrons. Protons have a charge, positively charged. Neutrons are neutral. And then surrounding the nucleus are electrons, and they have a negative charge. And so in general, we could argue that they move around here kind of like circling a sun or something like that. And there's specific amounts of electrons that can occupy a certain what they call shells or distance from the nucleus. And there's energy levels when they move and all that kind of stuff. But we're not going to get into that. We just want you to be aware that one thing about atoms that is useful is their atomic numbers. When we look at a periodic table of elements, we have an atomic number. And that number is also the number of protons. You can't change protons without changing the atom that you have. So if you have 6 protons, you're always a carbon atom. 1, you're always a hydrogen atom. 92, you're always a uranium atom. So once we change those, we change what we have. And so here's our periodic table, and we can look that oxygen is number 8, which means it has 8 protons in its nucleus. And of course, the way that it's set up here also determines how some of these atoms bond together to form new molecules. And when we talk about minerals, which is when we take these different atoms and we combine them together to form new things, there are a lot of them, and you just saw that in the previous slide. There, we could make a lot of minerals. There's probably over 3,500, I should say, sorry, 3,500 minerals out there. The good news is that there's about 20 that are super common, and there's a lot that are pretty rare, and you wouldn't, come across those in everyday life. And that's because if you look at this little chart here, this is the continental crust. But silicon and oxygen are the dominant elements that we have in the continental crust. So that wouldn't surprise you that the majority of minerals that we see have silicon and oxygen in their chemical formula, and that would be true. and we add some other elements to change and create new minerals. But the good news is we don't have to know 3,500 minerals. And so when we said we take two atoms and we bond them together, we get something new. And we could do that in a variety of ways, but it's just this idea of taking these atoms and arranging them in a way that they would like to bond together. That's based on sometimes the amount of electrons they have, the size of the atom, a couple other things that allow them to stick together and stay there, right? So, hydrogen and oxygen make water, silicon and oxygen make quartz, and so on. And they can be complicated, as you can see in that little feldspar example. So we're not going to go into how they bond, but just be aware, of course, that that's what we're making. We're making these minerals. So how do we know something is a mineral? Because obviously, as I look around my desk here, I've got a pen, I've got a mouse, I've got some glasses here. So how do I know they're not minerals? Because obviously they're made of different atoms and elements bonded together. So here's the criteria. So the general story is that it has to be naturally occurring. So it can't be man-made, so that kind of eliminates those things I just discussed. It has to be inorganic, which means it can't be alive, so my dog cannot be a mineral. It has to be a solid, so an orderly internal structure. And finally, it has to have a chemical composition that doesn't change. And so this holds true for minerals, and there's always some exceptions here and there, but in general, this is the criteria we would use to identify a mineral. So once we know it's a mineral, how do we know what mineral it is? Well, we actually look at the physical properties, because the physical properties is going to tell us something about its chemical composition. So when we add these things together, they have new chemical or new properties associated with them. And here's some examples here. Sometimes color is diagnostic, hardness, cleavage is the way something breaks, luster is how shiny it is, streak is the color it makes when it's scratched on a specific porcelain plate. Specific gravity is kind of the density, how heavy it feels in your hand. All of these things can be used to identify what specific mineral you have. Of course, as a geologist, when you're learning, you would have a chart or a book, and you'd go through, you're like, oh, this thing is blue. How many minerals are blue? Well, there's not a whole lot. So how do I know it's one of these 3 blue minerals? Well, I could look at how it's broken, or I could feel how heavy it is. Or I could try to test it to see if I could scratch it with a nail, see how hard it is. And that would eventually lead me to the name of that mineral. So when we look at minerals, there's lots of groups that we can say make up for the basis of these minerals. And here they are here. But once again, we don't want to get too bogged down in all the details. The thing we'll just kind of mention, and we already did, is that silicon and oxygen are the most common. So a group of minerals called the silicates are the most common because the silicon and oxygen are very common. And so when we look at igneous rocks, there's lots of silicate minerals that are in igneous rocks. And of all the rocks and minerals we talk about, the igneous rocks are probably the most important because they're related to volcanoes and things like that. And so they play a big role in that. And of course, how these things bond together give us some of the properties. And here's an example of silicate minerals that are all in our igneous rocks. Olivines, micas, feldspars, quartz. These are all the minerals that make up igneous rocks. And knowing something about how much is in each can tell us something about how it'll behave, potentially even how a volcano might erupt. So we're not going to go crazy on the minerals. We're just going to go into some common ones. So for this class, we should know what quartz is. It's silicon dioxide. It's very common. It's very hard, very resistant to weathering. Calcite is also very common. This actually weathers in that it dissolves over geologic time with water moving through it, and so it forms the rock limestone. And that can give us caves, it can give us sinkholes, and so we want to be aware of the mineral calcite. And same with gypsum and halite. Of course, we mine these things, halite for salt, gypsum for gypsum board, and things like that. But those are also things that dissolve readily in water. So we want to think if there's a layer of gypsum or halite in the ground, it could dissolve over time. We don't want to build structures on that. or if we're building a dam, we don't want to attach it to a wall that has minerals that potentially are weak or will dissolve over time. And then feldspars and micas, oh my gosh, I know the formulas are crazy, but these are really common in igneous rocks, and they weather out into clays and things like that. So those are kind of the ones that we were kind of focused on. So that was our crash course in minerals. Now we're going to blaze through igneous rocks. So we're definitely going fast and furious here. But we're just trying to give you a big overview, so then we can, in subsequent modules, when it's important to go back and, let's say, focus on igneous or sedimentary rocks, we can do that, okay? So the rock cycle is kind of this little diagram that shows how all the different rock types are connected. The idea of igneous rocks is that their definition is that they form from molten rock. So a process would cause the rock to become molten, and then that rock is mobile, it can move, and so it can cool at depth inside the earth, or it can make it to the surface and cool on the surface. Both are considered igneous rocks, but we give them different names depending on where they cooled. We typically use the term volcanic igneous to represent rocks that cooled on the surface, and plutonic igneous rocks are rocks that cooled inside the earth. So what we can do is use some features of the rock to tell us that. And one of the key things here is how big the crystals are in the igneous rocks that we discover. And so intrusive, another term for plutonic rocks, should have what we call coarsely crystalline or big crystals. Crystals you could easily see with the naked eye. And that would mean that what we're seeing here is this is a crystal, this black one here, another one, there's some kind of peach colored ones, there's some whitish ones, some gray. These are all different crystals. And so the idea is that in order for crystals to get large, we need to cool it slowly, and that occurs inside the earth, where it's got a lot of rock on top of it, insulating it. The heat doesn't dissipate as fast, and it cools very slowly, gives time for crystals to grow. Conversely, when it makes it to the surface, we call those extrusive or volcanic rocks. The minerals there are small. You can't really see them with your naked eye, although I know you can see these little dots here. Overall, they're fairly small, and the black colored minerals, you can't even pick them out because they're all very small. This just means that it cooled very quickly. So just a quick look at a igneous rock, we could make the call whether it's intrusive or extrusive, right? Just on its texture. And so that's how we're going to recognize, differentiate, and name our igneous rocks. We're going to use texture and composition. And so the story here is that we say the ones on the left here are finely crystalline, they have very small crystals. The ones on the right are coarsely crystalline. So the ones on the right must have cooled inside the earth, the ones on the left must have cooled on the surface. Then we also want to look at its overall color. And so what we would argue is the rocks at the top are darker and have more dark minerals, right? So a lot of dark color on the ones up top are darker, and the ones on the bottom are lighter. And so we don't have to identify specific minerals at this point. We just want to look at the color and kind of group them into whether they're really dark, or they're kind of in the middle, or they're kind of light. And so what we do is, we look at crystal size, tells us how fast something cools, and we're going to look at we're going to look at color, right? Light versus dark minerals. So if those two things you can do, then you can start naming igneous rocks. Okay, and so the overall color tells us its composition. It tells us what melted to produce that rock, so that can help us too. So the terms we want to introduce you to for igneous rock compositions is the term mafic, then the term intermediate, and then the term felsic. Those are the three terms we want to know when we talk about compositions. And so mafic rocks or magmas are ones that have a lot of iron and magnesium, and it makes them dark in color. Okay, and so when we see those, they should be like, think of Hawaii, the black lava that oozes out that is very mafic. So we look at that and say, oh, it's mafic and it cooled quickly, so the crystals are small. So mafic and it has small crystals. I go look at my chart and it tells me that the name of that rock is a basalt. Okay, and so we want to use that information to name the rock, but also know where did it come from. So it has a lot of iron and magnesium. That can tell us where the magma came from. All right, and so then when we look at our mafic rocks, there's also a term called ultramafic, which is very rare, but the ultramafic rocks we think are really mantle rocks. And so they're rocks that are down here that only come to the surface through some very unusual conditions. But the name basalt, which we just introduced you to, and the name gabbro, this is the finely crystalline version. This is the coarsely crystalline version. This one cooled at depth, this one on the surface. They both have the same composition. The only difference is their size of crystals. And we typically see this type of composition in the oceanic crust. So when we did the interior of the Earth, remember we said the oceanic crust is different from the continental crust. So oceanic crust is mafic. The mantle is ultramafic. And those are the compositional terms we would use to describe those. They're very general, but that's how we're going to identify these different rocks, by using their general terms. High in iron and magnesium, which makes them dark in color. Okay? And so we would typically get that from melting the mantle, partially melting the mantle. So when we have a divergent plate boundary, like you have just seen in last week's module, we're partially melting the mantle, and so when it cools and crystallizes, it's mafic, and that means it's making oceanic crust. The intermediate stuff is in between our felsic, which is the really light stuff, and our mafic, which is the really dark stuff. So intermediate kind of means it's in between. So it has some iron and magnesium, but it also has lighter colored minerals. So it has a little of both. And so where do we see intermediate rocks typically? We typically see those, and here's the same story. There's an andesite and a diorite. These are the names of these rocks that are intermediate. And in theory, this is the coarsely crystalline one, and this is the finely crystalline one. And I know these pictures don't really indicate that. There are big crystals here, I get it. But all the rest of this is super small. And so in order to be considered coarsely crystalline, we would argue that all the crystals are easily seen with the naked eye. If you can't see all of them, we'd still kind of call that finely crystalline. So andesite made it to the surface. Diorite never made it to the surface and cooled at depth. And we usually see these rocks show up in volcanoes or places where we have subduction. So we melt some of the material at depth. It mixes and it causes new material to come up that's an intermediate composition. And then we have felsic, which is our one that we would identify by color, saying it's the lightest or has the least amount of dark minerals. And so a granite, that's the name of the rock you've probably heard of. So here it is on the right. We have this granite, which is coarsely crystalline. We have a rhyolite, which is finely crystalline. What's the difference? Crystal size. This cooled at depth, this cooled inside the earth. We even have another version that's light in color, so we would say it must be felsic, but it has lots of holes in it, so we give it a different name because it tells us it's a different origin by the fact that it has so many holes in it. Okay, and so typically these compositions are found in the continental crust. And so mafic is oceanic crust. Felsic is continental crust. And intermediate is kind of a mix. Imagine if this crust here that's oceanic and there's a subduction zone here, it's a mix of the mafic stuff here and the felsic stuff here. As they mix together to form something new, we would get something in the middle, or if you like, an intermediate. Okay, and so here's kind of the example of that. I guess I should have waited for this slide, but here's some subduction. We cause the mantle to partially melt. What does that mean? It means it gives us a mafic composition. But as that molten material rises to the surface, it interacts with this continental crust that we said was felsic. So we get a mixing, we get intermediate. If it doesn't mix, then we can get felsic, where this material just sits here and doesn't interact with this, but just heats the continental crust, which is felsic, heats it enough that it starts to melt, and we end up with these melts that are just felsic. Right, so subduction usually leads to an intermediate, but it can also give us some type of felsic material. Okay, we're going to blaze through this because holy crap, we're running out of time. But here's the story I've already told you, right? These are light in color. We would argue they're felsic. We've got surface cooling, interior cooling. So big crystals, easily see with the naked eye. That's coarse, slowly cools inside the earth. Small crystals, can't see them easily with the naked eye. That cooled on the surface. We do have some unique textures like glassy. This suggests that it was quenched, cooled very quickly on the surface, so we don't see any crystals whatsoever because it cooled extremely fast. The holes that we talked about, so that sample that we showed you that was felsic, this is a mafic version. Why? Because it's dark in color. But they both have the same texture. So holes, or vesicles, tell me that there was a lot of gas in the magma chamber, and so that could potentially suggest that it was explosive, but it tells me there was lots of gas in there. And then we have this one called pyroclastic texture, and it is fragments of rocks that have been kind of welded together. This is something that happens on the surface from a violent volcanic eruption, and so we would use that to help us figure out that there was a very explosive eruption if we saw this type of rock deposited. And so the idea is that there's a bunch of different charts around. We would try to look at the chart and say, okay, is it felsic, intermediate, mafic, or ultramafic? So the idea of ultramafic, remember, is there's really only one rock, and it's the rock that has lots of green minerals in it, and it's called peridotite, and it's not very common. But in general, these are rocks that we would see on the surface a lot. And so what we would first do is say, what's the color? Is it really dark? Then it has to be in here. Is it really light? It has to be in here. Is it somewhere in the middle? It has to be in here. So over time, you kind of get used to these, but certainly in class, or if we were to show you some samples, we would show you, all three of these, and between the three, you could pick out which one was the darkest, which one was the lightest, and which one was intermediate. And then you could name them, because once you know their composition based on color, then you would just identify their texture, and then voila, you'd know their name. So light in color, fine grained, must be a rhyolite. Dark in color, mafic, it's also fine grained, that must be the basalt. What about the version that is coarse grained of basalt? Well, they're both the same composition, so gabbro must be the coarse grained or coarsely crystalline. And of course, we can interpret some things about them. Remember, we said the cooling rate is really what the crystal size is telling us, location, and potentially can give us some other information based on some unique textures like holes or like fragments that have been welded together. And so this is really the key, is that we would look at charts like this and try to figure out what type of rock we have just based on those two things. For us, when we talk about volcanoes, this is important here because we'll learn that this composition of igneous rocks is very fluid. It flows very easily because it has lots of iron and magnesium and a low silica content, where this material has a lot of silica, high silica, and the silica really makes it thick and gooey. And so very fluid means that when you have an eruption, lava can flow very far, like in Hawaii. Felsic means it cannot flow very far. So if there's gases in the magma, they get trapped in this felsic material, and they build pressure, and they can explode extremely violently, and so can intermediate. So our mafic volcanoes are the least likely to explode violently because of their composition. whereas intermediate and felsic can erupt violently because they have this thicker, gooier magma that traps all this pressure and gas. Pressure builds, and finally, right, we can get a big eruption. All right. Hopefully that wasn't too bad. It seemed like a lot, and this was only part one. So, minerals, rocks, those are the basics. Questions, comments, concerns, make sure you contact me.